Columns are the main vertical members in all types of building construction. The essential feature of a steel column is that it is a relatively long and slender structural member subjected to compressive loading. Other similar steel members can be found in the compressive struts of trusses and the supports of bridge structures. In buildings, the primary purpose of the columns is to transfer loads from the floors and the roof to the foundations. They hold the floors apart. They also carry horizontal loading from wind and even from earthquakes. Their secondary function is to support the cladding covering the building so that the enclosed space is weatherproof and suitable for its intended purpose. In steel frame buildings, most columns are fabricated from rolled H-section members. Standard sections are available from 152 by 152 millimeters to 356 by 406 millimeters in both mild and high-strength steels. Some structures have columns made of rectangular or circular hollow sections. These tend to be more expensive and more difficult to connect, but can have advantages in structural efficiency. Composite columns, such as H-sections encased in concrete or hollow sections filled with concrete, may also be used. In most situations, a steel column will need to be encased to provide fire protection. It is therefore rare to see bare steel columns in a building, although uncased columns are occasionally used external to the cladding. Because the primary role of the column is to carry the vertical loading to the foundations, the governing force in the section is usually axial compression. This is often accompanied by moments transmitted from the beams, produced by beam bending. The response of a column to applied compressive loads depends on the column's slenderness, related to the length of the column and its radius of gyration. The second moment of area, I, for an H-section, has principal values about the perpendicular x and y axes. Thus there are two values of the radius of gyration to be considered. Rx being the larger, xx is termed the major axis, and yy the minor. If a stocky column with low L over R ratio, say 30, is subjected to axial compressive loading, it gradually shortens until the material yields. For such a column, failure essentially occurs when yielding has spread over the entire cross-section and along the entire length. The load shortening response of the column reaches a plateau. This behavior is shown in a laboratory test. The top gauge gives the load on the column, the lower one the end shortening. Initially the load increases with only small elastic changes in length. After yield is reached, however, the load stays constant while the column shortens rapidly. If the column is slender, with a relatively high value of slenderness, the column will deform out of its line as the load is increased. This deflection starts in real structures by the presence of an initial distortion or out of straightness in the column caused by the rolling and fabrication processes. As the load increases, the lateral deflection increases non-linearly. As well as the geometrical out of straightness, the column has, in its unloaded state, residual stresses caused by differential cooling and hardening of the steel during the rolling process. The material at the junctions between the web and the flanges cools slowly, resulting in locked-in compressive stresses in the flange tips. When the column is loaded, first yield is reached under a combination of axial compression, bending caused by the lateral deflection, and residual stresses at the extreme fibre of the section. Increases of load beyond this level cause the yielded zone to spread across and along the column section. The failure of a typical column is illustrated in this laboratory test. The column is of medium slenderness, loaded by a hydraulic jack through a spherical bearing. A similar bearing provides rotational freedom at the top. The green line has been added to provide a reference. The column fails progressively by deforming into a half sine wave shape between the end bearings. The peak load is reached when the combined axial force and bending moment exceed the resistance of the cross-section. At this stage, further lateral deflection occurs with no increase in axial load. Despite the spherical bearings, some end restraint was present, causing a local failure to occur in the flange. The collapse load of a column is related to two limit conditions. A stocky column will fail by general yielding of the cross-section, and the column will squash. If a column slenderness is very high, higher than is found in normal fabrication, it will fail elastically without yielding. If it is initially deformed, failure will be accompanied by a gradual increase of lateral deflections. If the column is theoretically perfect, it will fail by buckling at the elastic critical load known as the Euler load. The Euler load is related to the column dimensions and material property as indicated by this equation. The limits of squash and Euler load provide an upper bound to the strength of a perfect column. The effect of imperfections and residual stresses reduces the true collapse load of the column below the upper bound. The reduction of strength is most marked in the region where the Euler load and the squash load are almost equal. The slenderness, L over R, which controls the column behavior and hence the collapse load, is the larger of L over Rx and L over Ry for the section. A single half-wave mode is only achieved for an elastic column when the ends are free to rotate in the failure direction. In this test, a roller support provides such freedom. The resulting failure is a single half-wave. The effect can be more clearly seen on these slender columns. The cross-bracing is provided to prevent translation of the column ends, a no-sway condition. The ends of the columns are effectively pinned by using V-shaped grooves in the supporting members. For this end condition, the buckling half wavelength is the same as the column length. The effective length is L. In reality, the connection of the column to the beam will have a finite stiffness and will provide some end fixity to the column. In the extreme, if the beam is much larger than the column may have a fixed or encastre end condition. This condition can be seen in this model, in which the column ends are built in. The lateral deflection is no longer a single half wave, but has zero slope at the fixed ends. The effective column length will, in this case, be 1/2 the actual column length, and the column will fail at up to 4 times the collapse load if it fails elastically. The effective column length is used with the design curve to calculate ultimate capacity. The column section will behave exactly as if it were a simply supported section with a length equal to the effective length. A further possibility for the failure mode exists if the top of the column is allowed to move relative to the base. In the model, If the cross bracing is not present, the column tops can move relative to their bases. They fail in a side sway mode at a much lower load. The effective length can become greater than the true column length. The effective length can still be used with the design curve to predict the column strength. The effective length will often be different in perpendicular directions, as will the radius of gyration. The relevant slenderness ratio for design will be the larger of the two. In this test, a pinned support is provided in the major axis direction, while the roller support about the minor axis is clamped. A major axis failure now occurs because the slenderness is greater in this direction. Columns are simple structural members, but even so, there are many factors which influence them. This video has shown some of the